All right, welcome to our unit on regression. Um, this is where things get interesting in terms of statistics. As we get into regression, we start getting into having statistics that give us the ability to compare the impact of different factors on an element of interest. And we get into the ability to do some predictions. Um, I am going to take this very slowly. I'm going to give you lots of examples. I'm going to provide annotated outputs from PSPP. I'm going to go in a little bit of a different order than what your book does. And once again, I am not going to ask you to work any regressions by hand. It I know that this is technically a math class, and your book spends a lot of time explaining how to work this by hand. You will never at any point in your career or in grad school work a regression by hand. It gets, I mean, you get more than 5 participants going, and it gets very complicated. And just I'm interested in you being able to tell me when to do which type of regression, how to be able to do it using the software, and how to be able to look at a regression output and put that in real world language to say, oh, here's how this is impacting this. Okay. So if you're enjoying the math of things, absolutely feel free to work out by hand those exercises it gives in your textbook. I'm not going to spend time working this stuff out by hand just because it is not a skill you will need for graduate school, for your career. It's good to understand the theory of where these numbers are coming from. I don't want you to just skip that textbook, that section in your textbook. You need to understand the theory of what we're doing here. I really don't care about you being able to accurately compute a regression by hand. I would much rather you spend the time rewatching this, going over the outputs, and knowing that you have a solid grasp on what we're doing here. So, regression. There are two different types of regression. There's actually way more than that. For the purposes of this unit, we're going to discuss two types of regression. There's bivariate regression, which you're only working with one independent variable and one dependent variable. In regression, they are called predictor variables. And well, when we get to this, we'll look at the predicted score, the actual scores. But a lot of times in regression, you will see the independent variable also referred to as the predictor variable, right? Because again, think logically, what we're trying to do is I'm saying that I believe that this variable predicts the result of this variable. Okay. So your independent variable is your predictor variable. It's the one that you're proposing. If I change this one, it's going to change that one. Okay. So binomial or bivariate regression, you have one predictor variable that you are working with. Multivariate regression, you're combining lots of different predictor variables and you're looking at their combined impact on your dependent variable. So we're going to go through both slowly. I'm first going to explain to you the math of what we're doing here. There's a lot of symbols and a lot of equations involved in regression. The main symbol that you need to know is this algebra looking thing right here. Y hat, and yes, that is actually what we call it. The letter Y that looks like it's wearing a little hat, we actually call it Y hat because apparently that is the level of creativity possessed by statisticians. Y hat is your predicted score, and we are calculating Y hat by saying we know that we have a constant number, we have a number to start from that we represent by the letter A. And what we're going to do is we're going to come up with a regression coefficient, a regression value, a regression proportion. You'll always see it called the regression coefficient or the slope that's symbolized by B, either a lowercase b or a capital beta. and we're going to multiply that by their predictor value. If that didn't make sense to you, that's fine. So what we're doing here is we're saying, I have a variable that I think has the power to predict another variable. For this example, we are going to use caffeine and anxiety symptoms among people who have an anxiety disorder diagnosed, okay? Because I'm sure you've heard this before, right? If you have problems with anxiety, if you have problems with panic attacks, don't be drinking 3 cups of coffee in the morning and 2 sodas with lunch and an energy drink in the afternoon and then taking a pre-workout before you go to the gym at night, right? You're going to start feeling like jittery and panicky, and it's going to be a problem. Caffeine, we know this through research. Excessive caffeine intake can impact the severity of anxiety symptoms in people who have a diagnosed anxiety problem. This is the example we're going to use for this, and I can give you my sources and cite my sources if you would like, but that is an established relationship. This data is made up. That is an established relationship. So what we're saying here is, I am saying with my predictor variable, my X, I'm proposing X, predictor variable, caffeine, independent variable, that has the power to predict the number of anxiety symptoms that a person with an anxiety disorder experiences the day that they consume them. I'm trying to keep track on my notes here to make sure I get everything I wanted to get. So this is what our X is. And then our Y hat, is our predicted score. This is the goal we want to get to say, I want to figure out an equation to be able to mathematically compute. Okay, so I think that caffeine has the power to predict anxiety symptoms. Let's put a number to that. I think if a person with a diagnosed anxiety disorder drinks or has 5 servings of caffeine a day, that their number of anxiety symptoms that day is going to be 6. I think if a person with an anxiety disorder has 8 servings of caffeine a day, their expected number of anxiety symptoms that day will be 10, right? I'm wanting to come up with an equation that actually lets me give some numbers there instead of saying, this is related to this, this makes this more likely, this can cause an increase in this, like what we've been saying all semester. I actually want to put some numbers to this. Your textbook gives the example of SATs and college GPA as saying, like, this is why so many colleges care so much about the SATs, because we've been able to come up with this equation and say, for every score higher than this that a person gets on their SAT, we can turn that around and predict that they will have this much higher on their GPA once they get to college. And that's why we care about SAT scores, right? So that's the example your textbook gives. So what we're doing is we're coming up with some math that lets us say, I have my starting point, okay, which is your constant or your intercept. I have my starting point, my constant, labeled as A. And I want to find out the number that I would multiply by the value of my predictor variable to translate into, so how many anxiety symptoms are they going to have that day? When you graph this out, what we're trying to do looks something like this. So I have my X here. So let's say that the X-axis, our horizontal, this represents the number of servings of caffeine. What we would do when we work out our math, which again, I'm not going to ask you to do by hand, but what we're doing when we work out our math is we're finding the point, first of all, of saying, okay, if someone has 0 servings of caffeine a day, they have none. They don't drink caffeine. No coffee in the morning, no nothing. Cold turkey, right? They wake up to a glass of herbal tea, which I've never understood, but apparently some people can do it. You have 0 servings of caffeine a day, and you have a diagnosed anxiety disorder. We want to find our constant, our baseline, our intercept to say, okay, so at 0 servings of anxiety a day, we're expecting a starting point, 0 servings of caffeine a day. we're expecting a starting point of 3 noted anxiety symptoms that day. That's our A. That's our constant. That's our starting point. What we're saying is we are starting from here. We are starting from A and working our way up. A is our baseline. Okay. In the example it gives in your textbook about SAT and GPA, it proposes a starting point for the GPA, right? This only works if we start here. Okay. So we have our starting point. We have our A. And ultimately, our goal in this formula is to be able to say, if I'm starting at 3, I'm proposing that I can figure out how many anxiety symptom scores I go up for every 1 serving of caffeine that I go over. I made this very simple and just made it 1-to-1. So to say I am proposing if I have 1 serving of caffeine, I expect a 1-point increase to 4 anxiety symptoms. If I go over another one and I say I have 2 servings of caffeine, I'm expecting another 1-point increase in anxiety symptoms. So that'd be 5. And what I'm trying to do is propose that number that lets me make those steps and say, for every increase that I have on this predictor variable I'm interested in, that's how much I'm going up above my baseline, above my constant, on this Y variable that I'm interested in, my dependent variable, my variable of interest. Sometimes you'll see it called a criterion a criterion variable. Your textbook uses that term a few times. Call it the dependent variable. We're good. Dependent variable. So your B, what you're multiplying by X, that is your slope. That is your regression coefficient. Your B is this dotted line between these 2 points. Your B is how much you're going up for each one you go over. It's the number 4. If I've gone over this many, how many do I go up? It can be a whole number. It can be a fraction. In this example, again, I just tried to make it clean and simple. It's 1. For every 1 I go over, I go up 1. If I had proposed that you had a 0.5 point increase for each step, right? So if I had said, I'm proposing if I have 1 serving of caffeine, I'll see 3.5 anxiety symptoms. Because, we'd average it out, means, all that. That number would be 1/2, 0.5. For every 1 that I go over, I go up 1/2. That is what your B is referring to, your regression coefficient or your slope. And then again, Y hat is your predicted score. Now, here's where, and again, remember, this is with our bivariate correlation, or with our bivariate regression. It's been a long week, guys. With our bivariate regression, we have 1 independent and 1 dependent variable. We're going to make this more complicated in a minute. But what we're saying here is I have my prediction, okay? I have my predicted score that I've got from my data. I have come up with a good fitting line of how I'm going to predict this to work. Let's say I actually take this out and I say I want to survey all college students in Missouri. I get a listserv of all the students in Missouri. I email all of them. I get lots of them to participate. Let's say I have 1,000 students that participate in this study who have been diagnosed with some form of anxiety disorder, and I get them to agree to monitor their anxiety symptoms and their caffeine intake every day. Okay, let's say I have 1,000 students I'm working with. Is every student that has 4 servings of caffeine going to have 7 anxiety symptoms? No, it's not going to be perfect, right? There is hardly ever any scenario where I could develop a perfect prediction that I could say I with 100% certainty, without a doubt, could tell you your score on this thing based on your score on this thing. It's just, it doesn't happen. It's not going to be perfect. So what do we do with that? And this is where a lot of the math of regression comes in. Okay, we've developed our line that we propose explains this relationship. And now what we do, and you'll see I've labeled the y hat, the predicted scores on each of these. So the predicted scores are the blue dots. I really need a better system for this, but I don't know what it would be. And we're going to take the pink, and what we're going to do is say, okay, so I'm thinking it's here, but now I'm going to mark how these scores are actually coming in. So I had this student who had 4 servings of caffeine and had 4 anxiety symptoms. I had this other student who had 4 servings of caffeine and had 10 anxiety symptoms. I had this student who had 8 servings of caffeine, and was way up here, like we would expect, like maxing out this chart. I had this student who had 2 servings of caffeine and only had a 3. I had this student who had 2 servings of caffeine and was up here at a 7. So what I do is I draw my line, and then I need to assess, okay, how far from these predicted values are my real scores actually occurring? And we watch that a little bit backwards, because if you were actually doing research and gathering data, what you would do is enter all your data. I'd enter all my 1,000 participants. I'd put it in my statistics software, and I would tell it, hey, come up with a line that fits as much of these as possible. And what would happen is it would come up with a best fit line if it was possible. And we have some numbers that we will get into when we look at our output. We have numbers that we can look at to say, okay, my software came up with a best fit line, and let's say that I have some more of these over here. Okay. Let's say that my numbers are kind of looking something like this. And remember, we visualized this when we visualized our correlation slopes before. Let's say maybe some of these are floating around out here. And my software would say, okay, I've come up with a best fit line for you. And actually in this, the line would be more over here, but you get what I'm saying. So the software would be saying, okay, I've come up with a line for you, but you need to be aware that your average data point falls this far from the line. And then that's something I would need to take into consideration, because I would say, I can predict that it will be about this, with about this margin of error. And we would do confidence intervals with that, which is a more advanced topic. But it would come up with a best fit line. Now, let's say that this was like all over the place, right? I had my dots everywhere. There was no rhyme or reason happening here. This was just like absolute chaos happening. Which that probably would still end up significant, but my software would come back with a not statistically significant result. And in the context of regression, a not statistically significant result would be saying, we can't really find a line that's a good explanation. Even if we allow for quite a bit of leniency in terms of how far your actual value would be from your predicted value, it's too far, right? This whole mess over here, it's too far. We can't find a line that gives you a good prediction for this. And that's what a not statistically significant result in regression is referring to. We can't make a line. It's not happening. It's not working. So in regression, the length from a data point, or the length from the expected value that a data point falls, see if I can find a color that'll show up. Red's probably going to look a lot like pink. But so this distance here, and this distance here, and this distance here. So all of these distances between the value I expected to see based on my equation and the value I actually documented based on what my participant told me, this difference right here is your standard error. And a lot of times that number is what's going to make or break whether you have a statistically significant result. Okay. Let me make sure I've covered all the terminology. So your constant is A, that is your fixed value or your starting point. Your regression coefficient is B, that's your slope. Your X is your predictor variable, your independent variable. Your Y is your criterion variable, your dependent variable. Your Y hat is your predicted score. Again, the regression line is how much the line will move up for each point you move over. And your error is your difference between your predicted score and your actual score. Now, there is a special type of regression that is called a standardized regression. So in this example, I was interested in number of anxiety symptoms a day and servings of caffeine a day. Okay? And I used kind of my raw numbers for that. You told me you had 4 servings of caffeine. The number I'm writing down is 4. You told me you had 6 anxiety symptoms. The number I'm writing down is 6. In a standardized regression, what we're doing is we're first converting all those things to z-scores. And there's pros and cons to doing that. It gives you a level playing field to work with, especially as we go into the multiple regression options. It gives you, if I'm measuring one of my variables in hours and one of my variables in intensity, I'm trying to keep a lot of things straight. Whereas if I have it standardized as z-scores, remember what a z-score does, I'm able to say for this many ticks above the mean, for this many ticks below the mean. And so I'm able to work with them in a much more apples to apples comparison rather than saying this is hours, this is intensity, this is something I'm measuring in number of centimeters or whatever it might be. So in a standardized regression, the main difference is up here, running out of colors, is up here instead of a lowercase b, you will actually see a beta. So we're going to use beta instead of lowercase b. And if you see a beta, that's how you know you're working with a standardized regression. The great thing about our stat software is it's going to do both. You put it in and it's going to give you your regular regression coefficient and it's going to give you your standardized regression coefficient. So you will automatically have both of them there. Let's see. Now, one other thing to be aware of with your theory of this, of what's going on behind the scenes before we actually get into any math. When we actually, you know what? I'm going to stop this video and I'm just going to do a new one for when we're talking about multiple correlations. Because I believe that is all the main elements of the bivariate correlation and the theory behind, or bivariate regression and the theory behind regression that you need to understand. So video 2 is going to pick back up with a discussion of when we do multivariate regression. All right. So as per always, email me with any questions about this. You can leave it as a comment on the video. I've linked it where I get emails about that as well, because a few of you have been doing that. So if you want to do it that way, that's fine also. But yeah, email me with questions. And video 2, we're going to start talking about multivariate regression. And then we're going to actually get into PSPP and do some examples.